Assalamu alaikum everybody. Welcome to our fifth lecture on the course Introduction to Artificial Intelligence. The title of this lecture is Constraint Satisfaction Problems. And here is the outline. First, we explain what is constraint satisfaction problem. Then we look at types of constraints and the main algorithm that is used for solving these kind of problems, which is called backtracking search. And then we look at heuristics that allow us to improve the efficiency of backtracking search. This includes minimum remaining values, MRV, most-constraining variables, MCV, least-constraining values, LCV, forward checking, and finally arc consistency. These are all different heuristics that helps to improve the efficiency of the ordinary backtracking search. So let's start with the explanation of what these types of problems are. What are constraint satisfaction problems? From what we have learned so far in the search lectures, a state is considered as a black box, as an indivisible item, and any data structure that supports successor function, heuristic function, and goal test can be used to store states in a normal standard searching problem. However, in constraint satisfaction problems, a state is not considered as a black box. In fact, it is consisting of a number of items. Every state will have a set of variables, xi, and a set of domains. So each of these variables will take values from a certain domain. Now the goal test in this situation is also slightly different from normal searching problem. Here a goal test is simply a set of constraints that specify the allowable combination of values for subset of the variables xi. So with this in mind, let's try to formally define what is a CSP. What is a constraint satisfaction problem? Okay, so a constraint satisfaction problem consists of three things. One, a set of variables, x1, x2, and so on until xn. A set of domains, d1, d2, and so on until dn. One domain for each variable, meaning the values that can be assigned to variable x1, for example, must be chosen from the domain d1. Okay, values for x2 will be chosen from the domain d2 and so on. So basically these domains will specify the possible values that can be assigned to the corresponding variables. Finally, a CSP problem will also have a set of constraints which must be satisfied for the problem to be solved. Okay, so we denote this as C. And then a solution to this CSP problem is basically an assignment of values, one for each of these variables, such that together they satisfy the constraint in this C. And these are some examples of constraint satisfaction problems. They are actually very widely used in many areas. For example, assignment problems, where, for example, you wish to assign teachers to teach courses in a university, for example. So the teachers in that case will be the variables, and the domains will be the courses that will be assigned to each teacher. And conditions could be that, for example, a teacher can only take a certain number of courses, and so on and so forth. Constraint satisfaction problems are also found in scheduling problems. Scheduling, for example, could include exams scheduling, where we have to allocate time slots to courses in an exam. Alright, so as you can imagine, in this case, the courses will be the variables, and the time slot that you would allocate to each course will constitute the domains. And a constraint, for example, could be that certain courses cannot be taken together because maybe students are taking both courses, and so on. It could also include assigning routes to public buses or trains, or even airlines, assigning takeoff and landing times for airplanes in an airport. These are all problems that can be solved, or that can be grouped under these constraint satisfaction problems. Okay, it's also applicable in factory scheduling, where you have, for example, assembly sequencing of, say, a car. Certain parts must be assembled together before certain others, and this must be done under certain time slot, and so on. Okay, so there are many application areas where this constraint satisfaction problem come into play. Hardware configuration, for example, is another, and even games, some of which we have already discussed in the normal standard searching, like Sudoku, 8 queens, 8 puzzles, and so on. They can also be considered under constraint satisfaction problems. Now, to make this more clear, let's take a specific example. Suppose we have a problem to color the map of Australia. Okay, we need to color each region with a different color. So you can think of the map of Australia as having these 7 regions. We have Western Australia, Northern Territory, Southern Territory, Queensland, New South Wales, Victoria, and Tasmania. So the idea is we want to color these regions with different colors, but such that no regions that are adjacent to one another will be colored in the same color. So formally, you can therefore define this as a constraint satisfaction problem where the variables are the 7 different regions. Okay, here we have shortened them like this: WA for West Australia, NT for Northern Territory, and so on. Obviously, the colors that are allowed will form the domains. So let us say we are only allowed 3 colors, either red or green or blue. Alright, then each of these variables will have the same domain, and the domain consists of these 3 colors. And the constraint, as we have just said, is that adjacent regions must be colored with different colors, must have different colors. Alright, so for example, we cannot have the color of Western Australia to be equal to that of Northern Territory. They must not be equal. And this is a possible solution. As you can see here, no adjacent regions share the same color. So this is a simple, complete, and consistent set of assignments that satisfy the constraints, and therefore it is a valid solution. So as we can see there, Western Australia is assigned the color red, Northern Territory green, Queensland is red, New South Wales is green, and so on. Yeah, notice the use of the word complete in the statement above. It implies that a state may be incomplete. If, for example, we haven't completed the assignment, only certain states are assigned but the rest are not assigned, then the solution is not yet complete, or that particular state is not a complete state. All right? But if you have done all the assignment, then it is said to be complete. Also, if the assignment is done in such a way that the constraints are satisfied, then the assignment is said to be consistent. Okay, so for us to have a solution, we must have a complete and consistent set of assignments. Okay, now a CSP can often be represented as a constraint graph, where the node represents the variables and the arc represents the constraint between them. So for example, our Australian mapping problem can be represented as this constraint graph. So as you can see, the nodes are the variables, and the links here, or the arcs, are the constraint. So this line here, or this edge here, says that the color of Western Australia must not be the same as the color of Northern Territory because they are adjacent. Okay, as you can notice here, the South Australia has the most connections because here, according to the map, it has more neighboring regions than the others. All right, so each border here is represented by an arc or by an edge connecting the nodes, indicating that the colors you assign here must not be the same as this one, must not be the same as this, and so on. Now, before we start looking at how to solve constraint satisfaction problems, let us explore the types of constraints, because there are actually different possible types of constraints that you can have in a CSP. The first and simplest one is called unary constraint. This is a constraint that involves a single variable. For example, if there is a constraint in our Australian problem that says Southern Australia must not be green. So obviously this constraint involves only one variable, and therefore it is called unary. Constraint can also be binary. So a binary constraint is one that involves two variables or a pair of variables. This is particularly the ones we have in this Australian mapping example. So for example, the color of Southern Australia must not be the same as that of Western Australia. So this is called a binary constraint. As you can see, there are two variables involved, SA and WA. You may also have higher order constraint involving three or more variables. We may not be considering this kind of problems in this particular lecture, but you should be aware that they exist, constraints that involve more than two variables. Okay, now having explained what are constraint satisfaction problems, let us now try to see how they may be solved. First, we note that the CPS have a special property, which is that they are commutative. What does that mean? It means that the order in which we assign values to variables does not matter. Alright, so for example, we could decide to assign green to Northern Territory first before we assign blue to Western Australia. Or we could do vice versa. We could assign blue to Western Australia first before we assign green to Northern Territory. The order in which we do the assignment is not important. All we want is that at the end of the day, all the variables should be initialized with values that satisfy the given constraints. And based on this property, actually, it turns out that CSP problems can be solved very efficiently using depth-first search, the same depth-first search that we learned in the last lectures. The only thing we do here is at each level of the depth-first search, we assign value to only one variable, and then go to the next level to assign the next value to another variable, and so on. If at any point we have an issue, for example, some of the constraints are not satisfied, then we backtrack to select a different value for the same variable that was assigned a value before, and then move forward. All right. Now, because of this backtracking feature, the algorithm for solving CSPs is actually called a backtracking search algorithm. But actually, it is nothing but a depth-first search with the condition that only one variable is assigned per level. Okay, so this is what I'm saying here. Therefore, such backtracking, such DFS that solve the CSPs, it is called a backtracking search algorithm. Okay, so this tree, for example, shows what we are talking about. Initially, we have not assigned a color to any variable. All right, so we pick one variable, and as we said, we will be assigning only one variable per level. So if we pick a variable, then we have three options. What color to assign to it? Is it going to be blue, is it going to be red, or is it going to be green? So whichever we decide, it is the one that we now going to explore next. So having assigned, for example, blue to our first variable, the second variable, what will be the color? Again, the options are the three possible colors: red, blue, and green. But the colors must be assigned such that they satisfy the constraint. All right. So if you keep doing this at each level, you will have just these three options. Of course, at any time you cannot satisfy the constraint, you have to backtrack and change the assignment and so on. You can see that the running time of the algorithm is going to be d to power n, where d is the size of the domain and n is the size of the variables. How many variables are we going to have? And therefore, actually, this is a very efficient search algorithm. Let us look at the algorithm in detail in the next slide. So this is the backtracking search algorithm. Obviously, it is a recursive algorithm, as depth-first search are normally implemented as recursive algorithms. So this is the main algorithm which the user will call, passing his CSP, control satisfaction problem. Okay, so it's called backtracking search, and it's going to return a solution if one exists, or a failure if it cannot find a solution. But this main algorithm actually is not the one that is doing the work. It's going to call the recursive one. So recursive backtracking. The work of this one basically is just to initialize our assignment set. So this assignment initially is empty. So you pass that along with the problem to the recursive version of the algorithm. It is the recursive version that will actually do the real work. Alright, so let's see how it works. So the recursive algorithm first check if the assignment is complete, then return the assignment and stop immediately. Okay. Otherwise, you're going to select a variable from the list of variables in the problem. So here we assume there is a method or there's another routine that will actually do the selection. It is called select on assign variable, where you will give it the variables in this CSP, the current assignment already done, and the problem itself. And it's going to return to you a variable that has not yet been assigned. Now you try to assign a value to that variable. So we have here a loop. Say for each value in order domain value. So again, we have another routine that will tell us what value among the possible values for this variable should we assign. Okay, so we're going to try them one by one. For each value among the possible values that can be assigned, check if that value is consistent with the assignment given the constraint of the problem that we have, then add that assignment to our assignment. Even as I assign that value to the variable and add this assignment to our list of assignments. Okay, and then do another recursive call with this updated assignment now as the input. Okay, if you are able to get so you're going to receive a result from this recursive call. Now you have to check this result. Is it not a failure? If it is not failure, then good, I just return it. But if it is a failure, then we have to actually undo the assignment that led to that failure. Okay, so here it says remove the assignment variable equal to value from the list of assignment, and then go and try the next value. And this is actually where the backtracking comes. So if we try a value, or if we try an assignment and that assignment failed, then we have to backtrack and try to do another assignment. Okay, so it's going to try another value, do the assignment, and then try again. If it works, that is fine, we are done. But if it doesn't work, then we have to remove it and then try again. All right, yeah. So if it works and all variables are assigned, we will never really reach here. We will never reach this return failure. One of the return result here will actually return the final result, because if you remember, each time the algorithm is checking if the assignment is complete, we stop. So one of the calls here will lead to that call. But in case we never really complete the assignment and we have exhausted all the possibilities, then this final return here will return failure. So this is basically the backtracking search, and it is the one that is used to solve virtually all CSPs. The only difference, as we shall see later, is trying to improve this backtracking algorithm to make it more efficient. And this is normally done in these two other routines that we shall discuss later. Select on assigned variable and also order domain values. These are the algorithms that will be used to improve this backtracking search. We shall see that later. But before that, let's take examples to make sure we understand how the backtracking algorithm works. For our Australian example, we start with a state in which no variable has yet been assigned. Okay, so we have an option. Let's say randomly we choose this Western Australian state. Remember, we said at each level we will be assigning value to only one variable. So we choose one variable, in this case just randomly, let's say Western Australia. So having decided that we were going to try and color Western Australia, we have three options. Are we going to color it red or green or blue? Because these are the possible values in the domain of each of these variables actually. So suppose we decide to go with red. Okay, so the next step is to choose another variable. Let us say we have chosen to assign value to Northern Territory. Okay, then you see that in that case we have only two options, only two color options, because of course Northern Territory cannot be red anymore. We have already used red as it is neighboring this Western Australia, so they cannot both be red. So the options we have are green or blue. All right, let us say we decide on green. Then we choose the next variable. Suppose we choose Queensland. All right, now Queensland again can only be one of two colors. It cannot be green because it is bordering Northern Territory, which is already green. So we only have options for red or blue. All right, so and so on, like that, eventually until we find a solution. I hope you get the idea. For example, assuming we accepted this, and then when we come to Southern Australia here, you will see that we have no option but to make it blue, because it cannot be red and it cannot be green. So this has to be blue. All right, so actually in the next level, I'm not going to show it, but if we are to show it, you will see that we have only one option, which is blue. And assuming this has been assigned to be blue, then this one can neither be red or blue, so it has to be green. Okay, and once we have this as green and this as blue, then this has no option but to be red again, and so on. So this is eventually how the algorithm will do this assignment. Okay, so we have seen the basic backtracking search algorithm. We have also seen how it works with the Australian coloring example. The question is there a way to improve on its efficiency? And the answer obviously is yes. There are general purpose methods, or if you want, you can call them heuristics, that can actually give huge improvement in the speed of the basic backtracking search. The key questions to ask if you consider that algorithm are: one, which variable should be assigned next? If you recall, we have, let me show you the algorithm. We have this method called select unassigned variable. At the moment, we are just choosing the next unassigned variable randomly. So the question is there a way to choose the next variable such that the algorithm will be faster? Okay, as we shall see, the answer is yes. The second question is, in what order should its values be tried? Again, if you look at this algorithms or methods, which will give us the next value to assign to the variable, which is called order domain values. At the moment, it is given the values just in the order they are listed in the problem: red, then blue, then green. The question is there a way to try these values that will make the algorithm faster? Instead of just starting with the red, is there a way we can choose another color that will make the algorithm to either terminate faster or to backtrack faster in case this is not going to lead to a solution? Again, the answer is yes, there is. All right. And then the other question is, can we detect inevitable failures early enough so that we don't waste time continuing the search when actually we know it's eventually going to fail? Again, the answer to that question is yes. So based on these three questions, we're going to find ways to actually improve the efficiency of the backtracking search algorithm for CSP problems.